Hey folks, welcome to Running a TV Network in the Cloud, CBS All Access on GCP. So before we go into the nitty-gritty, I just want to address a little background. And so I think one of the confusing things is when you think about CBS, you generally think about the television network that we are here to talk about. But CBS Interactive is actually quite a diverse company. We, as the slide demonstrates, we're in the top 10 for traffic, nestled right between Disney and Comcast. But our various brands, we have close to 40 different businesses under our umbrella, and it drives a tremendous amount of traffic. But today, what we're here to talk about is television. So before we get into it, what I want to do is just talk about at a high level what we're going to discuss. We're going to start off with where we came from, and this includes the TV industry itself, what it's like for us as a business operating in the cloud, some of the challenges and lessons that we faced from that transition. And finally, I want to talk about probably one of the biggest television events that happens annually, and that's the Super Bowl. So I wanted to talk about how we handled it, what the traffic looked like, and where we go with those sort of big tentpole events. So where did we come from? CBS has a rich history in radio and television. And we've done an impressive job moving into the internet space. CBS All Access is the first direct-to-consumer broadcast offering. And we have a lot of major television events that we support on our platform. The Super Bowl I just mentioned. We also have the Grammys, March Madness, that really, if you saw this last championship, it was pretty exciting. And we support our own original content as well on the platform. So shows like Star Trek Discovery and The Twilight Zone, as well as one of our bigger offerings coming back for the third season, which is The Good Fight. So one of the things that we have to do is that there are expectations around broadcast. And that is solving the always-on or always-ready problem. The expectation with any media is that it's there 24/7, it's available, and it's on demand. And what we're faced with is a background of really high product delivery. We've got about 100 years of innovation in the broadcast space already. And that's set the standard for what the expectations are for a company that is doing broadcast, whether it is through the traditional broadcast media or whether it is delivering that content over the internet. One of the things that we face is that we're constantly bombarded by rapid surges in traffic, meaning that we have to scale up very quickly. I mentioned some of these tentpole events like the Grammys or the Super Bowl. And it can be a big challenge to scale up so quickly. Live sports broadcasts that our sports team has to deal with and that we're often dealing with ourselves. As I mentioned, the March Madness, the championship there was one of the more exciting events in just the last week. So we get also call-outs for action. In previous years, the Academy of Country Music, their top award, the Entertainer of the Year, was decided on CBS.com. So that meant a tremendous surge of activity during the broadcast, where at 1 minute, millions of people would be watching the show, and then the next, millions of people are coming directly to our website in less than 5 minutes. And then we have the natural cadence of television. So CBS Marketing promotes our premieres, finales, special events, and this all can drive a tremendous amount of traffic to our platform. So where did we come from? And now I talked about the television broadcasting. What I want to talk about is traditionally our delivery of our platform. So we were in our own data center, and we had a service-oriented architecture. And what we tried to do is really abstract each of the layers of our platform, that they could communicate autonomously and that they were stateless. This allowed us to do horizontal scaling very easily at each level of our platform, whether that's our caching layer, our front-end layer, or our back-end. So one of the things, though, is that we had a single data center. We were not across multiple data centers, and it was a single zone. That comes with some advantages. One of the big advantages is resource predictability. So we were running VM there in the data center, and we generally knew what kind of capacity that we had and what kind of traffic we were going to expect. Predictable change control. In the data center, we work with the systems operations group, the network engineering team, to schedule any changes inside of the data center. If the load balancers needed to be swapped out for a hardware refresh, we knew when that was happening, and we knew we could act accordingly with our platform. The engineering expertise, as I mentioned, inside the network group, inside the systems operations group, we were able to really effectively leverage that expertise outside of our application engineering group. And finally, a simple cost forecasting. Whether it was hardware refreshes or models based on traffic growth, we knew what to expect in the data center every year through capital expenditures. So what were the drivers for the cloud? Why did we move from a model that was fairly predictable, that was easy to maintain, and we had a lot of expertise in? So one of them was the business expectations. As our application and the All Access product grew, there was an expectation for us to reach larger and larger audiences. And one of the things is that we didn't want to leave any money on the table when it came to growth. So we wanted to make sure that as we were expanding, we were capturing audience, and we were delivering the product that that audience expected. We wanted to maintain feature parity with our competitors. For good or bad, Netflix is the standard in this space, and we want to show that our product was a premium product and it can stand up to any of the players in the marketplace. So what were the technical considerations? I've already mentioned that we had a data center, and that's the single point of failure. So we had one pipe going in and that same pipe going out. If that goes down, our entire platform goes down also. Fixed capacity. We only had so much space, and virtualization inside of a single data center can only deliver so much capacity. And at the time when we made the decision to move to the cloud, we were reaching that capacity. The other part of it is that while the benefits of predictability are good, there's a real long procurement process to get new hardware swapped in and out. Moving to the cloud eliminates a lot of those problems. And finally, having that slowed capacity, single point of failure, and that long procurement process where we're trying to get updated hardware in place, it does slow down the application development process. Ideally, you want to decouple infrastructure from application development.
All right, thank you, Jason. So operating in the cloud, for us, it was really more about organization. we had massive cultural changes within CBSI as both a central group as well as within our vertical BUs. So we spent a lot of time investing in our teams to upskill them, introduce them to new technologies, send them to the right training programs. For us, just taking a step back, we're really looking at, just a year ago, and to some degree still a little bit today, we have a traditional operations team. You got one side of the team that's heavily focused on systems engineering, and on the other side, you got the application team that's constantly trying to rev and build out new products to meet whatever business demand, whatever the business demand might be. So the problem was it was also separated by a wall of compliance. You have one side that says, hey, you don't get root access, and you get the other side that says, come on, give me root access. I need to do this really quick. My product owner wants me to get this out the door really like tomorrow. So we had to kind of take a step back when we went to the cloud and look at where the engineering boundaries are going to be. We liked Docker. Docker was cool. It gave engineers the ability to start making some system configuration changes to some degree, and application server changes, and not have to go through an entire cycle of putting in a ticket, waiting for it to be scheduled, getting somebody to actually perform that task and come back and says, hey, can you guys check it out? Does it work? That entire process was extremely lengthy. It slowed down our ability to pivot. We just weren't as nimble as we could. So going into the cloud, we're like, okay, let's take a step back and let's understand what are we going to do to accelerate application development, but also maintain the compliance requirements that we need. So what we decided to do was, okay, within the confines of the container, go wild, right? And those of you that have worked with Docker knows that it's not really root, right? You get access to what appears to be root. It's pseudo root, right? So, and on the flip side, on the operations side, we said, okay, let's start putting some boundaries in place, because we don't want application engineers to say, hey, I need more hardware, more CPU, more memory, because it solves my immediate problem, and it spins up all the costs. We need to put some boundaries in place to manage costs and risk. So with our traditional ops team, we said, okay, so now, we don't want you guys aren't system engineers anymore. You guys have, you guys aren't maintaining systems per se. You guys have been building a lot of code to build out platforms for inventory management, or tools to augment our ability to do deployments, or things of that nature. You guys are engineers. You guys have been engineers all this time. You just weren't branded as an engineer. So we said, okay, why don't we take a bit of a leap of faith, and let's start to transition you guys into becoming more like SREs. SREs being people that are comfortable and focused on reliability, right? So these guys are the folks on our team that was at one point system engineers or SAs transitioning over, building out code to say, okay, we need to focus on, for reliability, we need to focus on observability. Okay, so we're going to go deploy a platform to start collecting metrics. We need to start looking at how do we make our infrastructure more portable, so that if we have specific issues, we can move things around. So our SRE teams have been, it's really a transition from traditional ops into more of a software space. So for us, we have both vertical SREs, meaning within our BU we have SREs, and we also have a centralized SRE team. The centralized SRE team kind of works very closely with our vertical SRE team. They kind of act as what Google calls, and I want to steal Mike's term here, they kind of act as CREs to our SRE team. So we have a perpetual cadence of stuff that we need to roll out that we're constantly trying to do. We leverage a centralized knowledge base of highly skilled individuals that help us build out whatever we need to build out, because they're smart people. Why did we choose manage GKE, or why did we choose GKE? Really comes down to priorities. Like I said before, we wanted to accelerate application development, and that was kind of our number one goal. And as Jason mentioned, it was really how do we allow individuals to focus on on the application and not so much the infrastructure. So we decided to go with managed GKE and focus on ramping up our teams, number one. Number two, redefine a focus on reliability. We wanted to make sure that we start adopting some of the practices around, hey, if you build something, it functionally works on your laptop, great. You deploy it, it doesn't work in production. What happened? So getting that instrumentation in place, getting that getting that instrumentation in place, using those reliability platforms that SRE teams are going to be building out, feeding that back into our organization, our engineering and product organization, to say, hey, this is a priority. You want this to work? Fix this, right? And often, when you're revving feature sets, you're not really paying attention to reliability. And I think reliability as an afterthought is how you're going to get in trouble, right? You don't want to think about reliability in the middle of the Super Bowl, right? Cost management. GKE, we've been able to leverage the horizontal pod accelerator autoscaler extensively, so we don't get that much traffic in the middle of the night. We ramp down our systems throughout the day. We have, we do have a lot of peaks and valleys, but generally speaking, we do also have a consistent oscillating traffic pattern. People wake up in the morning, they watch their news, they come online, they go to work, they don't watch TV anymore. They come to lunch, they might pop on and tune into their favorite show, catch 15 minutes of that, and so on and so forth. And of course, for us, we have multi-cloud ambitions. We definitely believe that you shouldn't put all your eggs in one basket. That's why we built a horizontally scalable platform. That's why we have focus. We focus on SOA. We want to make sure that if in an event that we have a high-profile event, tentpole events, we do have the ability to say, hey, this is not working for whatever reason, let's go somewhere else. Considerations, it's easy to use. I think most of you guys that have experience with GKE realize how easy it is to pop it in, run a few commands, and next thing you know, you have your service up and running. Frequent updates. We want to make sure that we leverage the experts as much as we can. Google has managed GKE deployments forever. So we want to make sure that that we're getting as many updates to the platform as we can without us having to do any work. And of course, we have the thorough support of the Google engineering support team, and as well as our technical account managers. They're constantly pinging us and saying, hey, how are you guys doing? Do you have any problems? Do you have any features that you want us to evaluate? Having a managed service allows us to provide that feedback and have leverage the Google, the massive resources that Google has to do that work. Challenges. So I'm the problems guy. So the cloud wasn't that easy. So when we went from a data center, as Jason mentioned, it was a single zone, single data center, single point of failure. Moving into a multi-zone environment definitely had its challenges. So first, when we were moving over, we said, hey, we have this monolithic application. What can we do to tease this apart, identify pieces that can independently scale, we can independently attach cost to it. So we spent a lot of time finding candidates for transition. SOA obviously made it a lot easier. Since we're already service-oriented, it made life a lot easier for us to identify the pieces that we could move over. We didn't want the lift and shift. We obviously went into containers, and we integrated with many cloud-managed products as it fit within our architecture. There's some things that didn't, so we ended up refactoring our code base, roughly about 20 to 30% of our code bases to accommodate for some of the integration points. We want to make sure that like we had this one service that we forked off, and it's really a kind of an isolated feature of a digital asset management system. It resizes thumbnails. It's historically, the source code was built to work on a file system, NFS. On the cloud, yeah, I can have NFS. I wouldn't make people very happy, but I can have NFS. But it's more appropriate to integrate with Object Store. So we ended up gutting a lot of that code and doing a direct integration with Object Store so that we can also have the ability to the regional distribution of our assets and all that fancy stuff. Monolithic to microservices, straddling between the data center and GCP. We didn't do a single hop jump for our cutovers. We actually ended up teasing apart roughly about 8 microservices and slowly started moving our products up into GCP. So we had concerns about Dockerization. We had concerns about, like, is Kubernetes going to work for us? What happens when things fail? Can we induce failure, and how do we respond to those failures? We had questions about all that stuff. So what we decided, so we started teasing apart these microservices, moving them up one at a time, and just kind of building up our own skill set. And of course, we had problems. That's a bad look. So for us, it was really more of a cutover problem. So we'll go back to the thumbnail resizer. We tried to pre-cache as much as we could. We knew that, so these are the dynamic resizers, so when you make a request, it goes and says, hey, I need this asset at this size, and it goes in and makes it, and it caches that asset and makes it available. It doesn't resize multiple times. So we tried to pre-cache as much as we can. We loaded all of our apps, we ran through all the permutations. Things were great. The applications work. We were able to validate that. But we miscalculated how many people are hot linking our assets on the internet. So what happened was, as soon as we flipped over the DNS, we had a tremendous amount of traffic that just hit us. So luckily, because we were on Kubernetes, we leveraged the cloud to allow us to, the cloud has all the resources in the world, so we just scaled out as big as we could to absorb that traffic for a week or two. And then as the assets were cached, we started bringing down the cluster. But without having a fixed infrastructure, you wouldn't be able to do something like that, right? You wouldn't have all these resources at your fingertips, and So the internal load balancer. Traffic distribution is tuple-based. It does not account for utilization on your back end. So this one kind of bit us a little bit. We are accustomed to a stateless SOA application, right? So we expected this load balancer to just absorb our traffic, round robin our traffic to our backends, and awesome, right? Well, that didn't quite happen. So because they're tuple-based, if you have connections that, if you have services that make connections to these services, and they're persistent connections, they would linger, and they would stick and be fixed onto a specific node until that connection dies. But because we're trying to optimize and not make a bunch of HTTP requests, we decided to use persistent connections, and it just kind of created a scenario where it was leaning on 2 of our services. All right, in this case, we have 4 machines, or 4 pods, and over time, in the beginning, when the systems restarted, the connection pools were hydrating. They made a bunch of connections. Everything looked great. 20 minutes later, we get this. So obviously what happened here was that backend services with persistent connections lacked the entropy necessary for even distribution. So we weren't able to get even distribution with the ILB as it stands today. We did reach out to Google. Google did come back to us and say it is a feature request, so if any of you guys have this problem, please reach out to your TAM. We did, but because we can't live with this, we obviously had to do something. So we decided to think about what happens if we scale out. If we scaled out, we would be able to create more entropy, right? Because the tuples would have more entropy, therefore the load would be more distributed. But over time, it will eventually lean against one or two pods anyway. So that wasn't really a solution. Application load balancing. So we said, hey, maybe we can just do this ourselves. Forget using the IOB, or allow the application to make requests directly to whichever backend service. Well, the issue here is, because we're in the cloud now, resource limitations is not an excuse I can have anymore. We need to be able to support autoscale. When you do autoscale, you have to figure out a means for discovery, for those resources to, that come online, they become available. We have to be able to inject that into our application. Do we really want to reinvent that? So lastly, we said, okay, maybe we can roll our own load balancer. We looked at products like HA proxy and a bunch of solutions like that, and we ended up using the Nginx ingress controller. And what this allowed us to do, now this still uses the IOB, but what happens is the Nginx, so the leaning happens between the IOB and the Nginx ingress controller. But within Nginx, it's smart enough to understand that, hey, I need to make equal distribution across the nodes that I'm aware of. And so the balancing ultimately fixes itself, right? So more problems. Zonal dependencies and kubedns. So going into data center to multiple zones, when you have a relational database, and maybe some of you guys use MySQL here yourself, you have a master and you have a bunch of replicas. So you have to put the master somewhere, right? So it's either going to be, in this case, A, B, or C. And you have a situation here now that if your application is running in zone C and you have a dependency on zone A, if zone A goes away, that's problematic, right? So we need to kind of fix some of those questions, some of those problems. We looked at kubedns. Like we said, okay, kubedns is cool. It understands when services become available, and understands where the backend services are. It goes and distributes that. But kubedns has, distributes across all the zones. So when that happens, that's not really what I want. I kind of want a scenario that kind of looks like this. This is a work in progress, so I don't have I can't sign off on a full solution yet. But we want to be in a position where we are zone independent. So if we're zone independent, it means a request that goes into zone A stays in zone A, gets processed in zone A, and if that zone goes away, cool. We'll just cordon off that zone, drain all our backend services out of that zone, and move on. So in order for us to be zone independent, we have to move on to HA databases, high availability databases. So we use Redis pretty religiously. So we started thinking about, hey, are we going to use the clustered Redis? Are we going to use Redis backed on Sentinel? Or do we just deploy a bunch of different Redises and just make the application aware that they need to call specific CNAMEs for, so that the traffic can stay within the same zone? We looked at cloud managed products like Spanner and Cloud SQL. Unfortunately, they're regional, so we didn't want, or at least Cloud SQL is regional, and we didn't want to be tied to a specific region. We wanted to be able to be in US East and US West. We are using Bigtable for a feature set. I'll come back to that. But we ultimately wanted to be cloud neutral. We wanted to make sure that we selected a database that allows us to span multiple regions, multiple clouds, and so we are evaluating CockroachDB. To maintain traffic within a single zone, we are looking at service meshes. We haven't quite gotten to the point where we can thoroughly talk about this yet. We're still evaluating whether or not Istio or any other competing product is the right product approach, but we are looking at service meshes to do that. And obviously, we have a lot of decisions to make. Lessons learned, plan for failure. All of our desire to be zone independent, be cross-regional, multi-cloud is because we want to make sure that we have the capability of failing out of a zone. We have to make sure that we have a DR strategy. Really focus our teams on setting up reliability as a product. You got to build, you got to instrument, you got to evaluate, repeat. Everybody's responsibility. Focus teams on too much instrumentation, no way. Create a feedback loop. I think this is one of the bits about building out a SRE culture. It has to be, you have to be in a situation where you have a blame-free culture that allows instrumentation to get surfaced and not have the person that's reporting the issue be blamed for X, Y, and Z. And it has to be well absorbed by the product engineering organizations, and it's a team effort. That's the bit about SLO and SLIs here, and let Jason talk about the Super Bowl.
Yeah, so Hanson touched on a number of things, and I think one of the most important things to really to emphasize is the cultural shift when you move from systems operations groups to an SRE mindset. And one of the first things that comes up is collaboration with Google and their SRE team. I can't overstate this enough that one of the benefits of working with Google Cloud is that Google really does want to become partners with all of the teams that come on board their platform. And that means really understanding our application, really understanding what our problems are, and trying to help solve those problems. One of the things Hanson talked about with the GKE component is that there is a virtuous feedback cycle with Google where we give them feedback about our problems with their products. They go back to their product and engineering teams to really focus on a lot of these problems and improve the services for their customers. So when we talk about Super Bowl, it's not just our team getting ready for it, it's Google also getting ready for it. So we spent months working with the Google team getting ready for this launch. And what that meant is working with our TAM, our technical account manager, working with the support team there at Google. And we really gave them an in-depth understanding of our platform, how our service-oriented architecture worked, and all of the different platforms that we were serving this content on. I'm going to pause for a minute and talk about that because I think there's one key differentiator in our product in comparison to a lot of our broadcast competitors that are starting to come online. And that is that we have over 200 affiliate stations that have their own local streams. So we're delivering the local CBS station regardless of where you are in the United States. That means that all of those stations have to be up. We have to have an operations team, and we have to have a culture that makes sure that all of our customers are receiving the product that they want. So the Super Bowl itself, now I've mentioned the 200 local affiliates. So it's not just one stream that we had to worry about. It was 200 plus separate streams. And this includes backup streams as well, because one of the most important considerations here is mitigation and disaster recovery. On any event this size, with your audience expectations, you better be prepared for something to go wrong. So what we saw on the day of the Super Bowl was greater than 17 times our normal traffic. And you can see how these requests spiked up during the day of the Super Bowl. Now, we had pre-planned, and as I mentioned, one of our big challenges around these tentpole events is that we can have very rapid request growth in an extremely short amount of time. So always being prepared for that and not relying on auto scale is probably a safe bet. So before the event, we scaled up 14 times our infrastructure. And over the course of the event, I would say about 3x of the additional scaling was then managed by the autoscaler. But that gave us the ability to really absorb that initial request hit that our systems took without missing a beat on delivery. Now, the good news here is that calculating that scale was pretty easy. What we saw is that one core was about 50 requests per second, and we were able to do the math and scale accordingly so that we were able to deliver at a really high quality level. Some of the considerations that we had to take into account besides just the massive number of requests was scaling our backend database systems. Hanson showed you a little bit about some of our current challenges. Well, what we had to realize is that as we scaled horizontally, each of those cores taking up 50 requests per second, that we had to scale those connections to our database in order to handle the amount of additional load that it was going to receive. So we had to consider the upstream services and just the fact that more pods is going to equal more connections to those database systems. So especially when you have a single point of failure like we did with our master, it's a really important consideration when you're thinking about scaling up your systems. I'm going to give this back to Hanson, and he'll finish off with some of the best practices.
All right, so we got some to kind of close off. We have some best practices, some best practices listed here. Number one, test your infrastructure, please, because if you don't test it, you will never know. So especially your critical services. Work with your TAM. Your TAMs are there to help you. So if you, for us, we had a situation where we say, hey, we're going to get all this traffic. Do we have enough resources allocated to our accounts so that we can, we can scale to that point if we needed to. So work with them to define, what you believe is the amount of are the amount of resources that you need, and they'll make sure it happens. 100% engage with your CREs and SREs. Treat them as if they were part of your own team. Do your architectural reviews. Make sure that they understand how each component actually works, where your single points of failure are, if any, and where your most critical components are. Share your instrumentation. The Google team has a lot of instrumentation behind the scenes that can really augment your perception on how things are actually running from your metrics. And runbooks. If you don't have runbooks, create them. You have to plan for failure. So if you are going to get yourself in a situation where you may lose a master database, have a runbook entry in there that says, hey, if this falls apart, what do I do? Who do I call? Who do I scream at? Product development life cycles. We have to incorporate reliability. And it's going to be a perpetual cycle. You're not going to be able to get around that. Because the whole point of planning for failure, disaster recovery. At the very least, have a plan. For us, we have ambitions of going multi-cloud. Hopefully, that will help us, effectively have a disaster DR strategy. Yeah, I think that's it.